All right, so starting a new chapter here, and now we're kind of getting into more of the calculus. This is going to set the stage for what we're going to be doing for pretty much the rest of the semester. Measuring change is the basis of pretty much all calculus, and especially the differential calculus that we're going to be doing for the next couple of months. So let's start with this idea of average rate of change. So average rate of change is really just slope. And so what we're doing now, what you do in calculus is you're measuring slope, you're measuring instantaneous slope. So if we're talking about a linear function, of course, the slope is constant. Linear functions have a constant slope. But if you're talking about any other type of function, the slope is always changing. So you have some polynomial that looks like that. Here we have an increasing slope. Here we have a decreasing slope. Here we have another increasing slope. And it can always be changing. So we have a square root function. You can see it flattens out, have a steeper slope here, and then the slope goes down and gets closer to zero here. So all we're doing is we're building up to where we can tell what is the slope of the tangent line at this point. So if we were to kind of draw a line like that, what would the slope of that line be that touches right there, or wherever we want? So you'll notice this average rate of change over the interval x1 to x2 is a difference quotient. Remember the formula for slope when you learn about linear functions is rise over run, change in y over change in x. That's all this is. So we're just looking at 2 points, and the difference here is now we can kind of talk about this with any type of graph. So maybe here is A, here is B. What is the average rate of change? We're just going to find the slope of the line that connects those 2 points. That's all we're doing. So if we look at this first example, compute the average rate of change of the function 4t squared minus 3t over the interval 2 to 5. So we need to set this up as g of 5 minus g of 2 over 5 minus 2. And so we can just plug in 5 for t. We can find g of 5 is 85. And we can find g of 2 is 10. And 5 minus 2, of course, is 3. So we end up with 75 over 3, and that gives us 25. Okay, so every unit, and maybe t is representing time here, every second, or whatever unit of time we're looking at every second, this function g is changing positively by 25. All right, so let's look at more practical example here. The population in Aruba is given in the table below. Compute the average rate of change from 1975 to 2010 and interpret the results. So we have 1975 here, 2010 here. And so sometimes you'll see this average rate of change. So we can just write it like that. And so this would be, so we'll just, actually, we'll call it P. We'll call the function P since we're talking about population, but I mean, it doesn't matter that much. So P of 2010 minus P of 1975 over 2010 minus 1975. And so P of 2010 is 104.6. P of 1975 is 59.2. And then 2010 minus 1975 is 35. And so we put that in the calculator and we get 1.297. And so the population here, so that would be 1.297 units of population per year. And here the units of population is thousands. So we could convert this to 1297, because the population is measured in thousands. So the interpretation here would be, and I'll write it out just for the sake of time. We could say that the population is growing by 1,297 people per year on average. And so so really, when you interpret the average rate of change, think about what the units for the slope would be. So, and you get the units just It's just the Y units per X unit. So then we can do part B. And from 1975 to 1970 to 1965. So average rate of change is P of 1970 minus P of 1965 over 1970 minus 1965. And so in 1970, it was 59. In 1965, it was also 59. And so then over 5, let's scroll this down a little bit. 5, and of course that's going to be 0. So the population was constant between on that interval. All right, so we'll stop here and come back on the next one and finish.